In this work, we investigate the application of the transformer to the keyword spotting task. The transformer is a neural network architecture based on the self-attention mechanism, which is now dominating the machine learning field. It was first introduced for the task of natural language processing, and recently it has gained more attention in the field of computer vision. Inspired by this recent progress, we investigate whether transformers can match the performance of conventional network architectures, such as convolutional or recurrent networks, for classifying short snippets of audio. We reuse a typical keyword spotting pipeline and replace the conventional architectures with a sequence of transformers. Given a raw audio waveform, we first compute the Mel-scale spectrogram. We then split the spectrogram into non-overlapping patches in the time domain. We then project each patch into a higher dimension, add a unique learnable positional encoding for each patch, and append a classification token. All the patches are then fed into a sequence of transformer encoder layers, which consist of multi-head attention operations as well as multi-layer perceptrons. At the final transformer layer, we fetch the classification token and use it for linear classification among the set of keywords in the dictionary. During training, we also consider knowledge distillation from a non-transformer teacher to improve the accuracy of our model.
Our results show that the keyword transformer achieves state-of-the-art performance on the Google Speech Commands task. This was surprising to us because we tried very hard to stay close to the DAIT architecture and hyperparameters, and also compared against a very strong convolutional, recurrent, and multi-headed attention baseline. In fact, our baseline was substantially state-of-the-art because we found a better training schedule during our experiments. Despite this, the keyword transformer makes 17% fewer errors than that on the 35-word task. There are a few mysteries in our results that I'd like to share. Firstly, we discovered that, in this case, post-normalization consistently performs better than pre-normalization. And we were very surprised by this. All of the literature suggests pre-norm should work better than post-norm, and we expected to find that too. This effect was small, but was too persistent to ignore, and is perhaps worth some further study. We were also surprised to find that the keyword transformer to be latency competitive. We didn't design it with latency in mind and performed no architectural sweeps to optimize these figures. So we believe there's actually a lot of headroom here for further improvements. The second mystery here is, why do these models improve on the 35-word task relatively more than the 12-word task? Is the simpler task saturating on complexity, or is there perhaps something about the unknown class that is less optimal with attention heads? We don't know. Overall, we're proud to present the keyword transformer, a simple model that achieves state-of-the-art performance on the keyword spotting domain.